Welcome. And now we find ourselves at topic 14.1 in our journey through the world of physics. What you will find is that topic 14.1 is eerily similar to option F.2. And so I'm going to encourage you to go watch the F.2 video because I'm going to be skipping over all of the sections that are identical in this clip. And so you may find yourself being lost if you have not already watched topic F2. I'm going to pause for a few moments while you go and do that. Welcome back. I hope you enjoyed watching option F.2 as much as I enjoyed making it. Now, to proceed with topic 14.1, we're going to start with signals. And we're going to go past signals because you should have already learned about signals in option F. Analog signals, should have learned about. However, let's talk a little bit about vinyl records because vinyl records are awesome. Vinyl records are a round piece of vinyl that has a whole bunch of scratches in it that a thin needle runs over and reads. If you were to look at the surface of a vinyl record, you would see that it looks similar to this. This is an analog storage device. The depths and widths and breadths of the grooves that exist on a vinyl record have an infinite number of depths and lengths and breadths. And so the sound generated by a vinyl record can have an infinite number of frequencies and tones, and it's a much fuller sound. And as the needle moves around it, it moves through these grooves and reads the signal and converts it into a sound. If you've never listened to a vinyl record, I urge you to do so. Your life is not complete unless you have. If you have, kudos to you. You're further along than many. But this is an example of an analog storage device because there are so many variations in the signal that it's definitely going to be an analog. Another one is the audio tape. While still out of fashion as is the vinyl record, the audio tape doesn't have quite the nostalgia, I guess, of the vinyl record, and we're probably not going to be clamoring to bring it back. Much like the 8-track, it had its time and now its time is done. The difference between an audio tape and a vinyl record, however, is that instead of varying grooves, we have magnetic fields. And so within the tape recorder, perhaps you've seen one, there's a small electromagnet, and that electromagnet can vary the strength and direction of the magnetic field on the magnetic tape that composes the audio tape. And so as that audio tape is then fed back through the tape player, there's another electromagnet that responds to the electric fields in that magnetic tape. And so the magnetic fields that have been established on the audio tape actually create a current in a very tiny electromagnet that's inside the tape player, and that's how it's read. So it's kind of a cool application of electricity and magnetism. But again, analog signal. You should remember from F.2 that our digital signals do not vary with time. It's either on or off, 1 or 0, up or down, left or right. There's only 2 options, and that's how the signal is determined. So we're going to move through this quickly. We talked about converting and binary. This should all be review. So we're not going to spend much time except to look at the beautiful color spectrum that's on this particular slide. Quite enchanting. We talked about analog to digital conversion in option F.2, so again, we're not going to spend time here doing so. Feel free to refer back to video F.2 if you need a refresher on any of this content. Sampling rates. I remember you fondly from F.2. But here we have something new. Storage on a compact disc. For in fact, CD stands for compact disc. In 30 years, that's going to be one of those rare pieces of trivia that wins you money on Jeopardy. So, our basic structure of a CD is that there's some top coating that consists of the label. Then there's some acrylic in there that's for protection. You have a thin piece of aluminum and then a thicker piece of plastic. And in a CD that's created at a manufacturing plant, the pits that are in the CD are actually pressed in. They are put under a machine that has the inverse arrangement of pits and bumps, and it's actually pressed into the aluminum, so it's physically in the aluminum. And so the information is stored on the CD as a series of bumps and flats that's recorded in the metal, which is then covered up by the plastic to protect it. Uh-oh. The CD is read. There's a laser that shines along the tracks, and the light gets reflected off of the flat sections, and it's read as a 1. If the pits or bumps are at the right depth, when there's a light shown off of a pit and a bump, they will actually destructively interfere with each other, and the laser reader will read it as nothing. There will be no light that comes back on the laser reader because they're going to destructively interfere, and at that point it's read as a 0. And so in this way, the laser can read the series of 1s and 0s, the binary code, which is then converted into the signal which you hear from your speakers. And remember that for destructive interference to occur, the crests and the troughs of any given wave must line up exactly. And this happens when the waves are half a wavelength or pi out of phase. Okay, so when they're out of phase by half a wavelength, which we know is pi. And so you see your resultant wavelength then is this flat line with 0 amplitude. But how deep do these pits need to be? Great question. The average wavelength of our red light that's used by a CD player is about 700 nanometers. And so if this is the case, then we can very easily calculate the depth at which our pit needs to be. Remember that as the light travels down, let's use a red light, we have some light traveling here that gets reflected off the top of our bump. We then have other light that travels down and is reflected off of the bottom of the pit. In order for our wave to be out of phase, there has to be a half wavelength difference between the two waves. And so because this wave that goes to the bottom actually travels to the bottom and then back up, it travels a distance 2d, where d is the depth of our pit, further than light wave 1. So if the blue one is 2, the red one is 1. Number 2 travels 2d further. It travels a distance further by a factor of 2 times the depth of that pit. So that means that 2 times the depth of the pit has to equal 1/2 the wavelength. Or, look at it another way, the depth of the pit has to be 1/4 the wavelength of the wave being used. And so if our wavelength is 780 nanometers, 1/4 of that is 195 nanometers. So the rough pit depth on a CD is about 195 nanometers deep. Here's another nice diagram to kind of show what's going on. If we look here on the right, you can see that from our laser we actually have the beam, part of the beam hitting the edge here and being reflected back to the sensor. The other part going past the edge of the bump there, traveling to the bottom of the pit and traveling back. So this number 2 here is traveling 1/2 lambda further than the first wavelength as we just showed. And so that causes destructive interference. So what that means then is that the zeros are actually read anytime there's a change in depth. So whenever the bump goes to a pit or the pit goes to a bump, so the starting and end of the pits are zeros, and everything in between is ones, or are ones. Now if we compare CDs versus DVDs, what we find, and you've probably noticed this, is that DVDs hold a lot more information. Your average DVD can hold almost 5 gigs of information, while CDs can only hold about 650 megs. The reason for this is that DVDs use a different light. DVDs use light that's about 650 nanometers rather than the 780 that CDs use. Because it's a shorter wavelength, it means that the pits don't have to be the same depth. They can be thinner. It can pick out smaller changes in the depth, and so you can make those pits thinner, which means you can fit more pits and bumps on a CD along that length, so you can include more information. Remember that if we're reading changes in pit depth, then the number of pits and bumps on the CD is what's going to determine the number of ones and zeros, which is then going to determine the number of, or the amount of data that can actually be held. Now, the only thing, because we've already talked about this and component mention, just because it's kind of interesting, when we're talking about CDs and DVDs and we put them into a burner. So you got your computer and you're burning a mixed CD. I don't even know if we burn DVDs anymore. Now you just share your iPod playlist. But there was a time when you could put a blank DVD into a DVD burner and record information on it. Songs, papers, files, whatnot. Well, with our DVDs that get made in the factory that have the DVD press that has all of the little bumps that get pushed down into the aluminum on the DVD, the actual laser beam has that destructive interference so that there's no light being sensed at the sensor. DVD burners can't obviously press into the actual aluminum of the DVD. They do actually burn the surface. And so inside the DVD burner, there's a little laser that shines on the DVD. And at places where the DVD needs to read zeros, it'll actually burn a mark on the DVD so that all of the laser light is absorbed at that point and none of it is reflected. And so instead of the lack of light occurring because of destructive interference, the lack of light being received at the sensor actually occurs because of the burn mark on the CD or DVD that absorbs all the laser light. So you're still getting the same idea. You're still getting the same effect where there's no light that's being sensed by the sensor. It's just the cause of it is changing. Instead of changes in pit depth being used to represent zeros, it's actual spots that are being turned black on the DVD or CD that absorb all the light so it doesn't reflect back to the sensor. So a little bit different approach, but it does the same thing. And that's also why burn DVDs don't last as long, because that burn mark can get scuffed off or things can happen to it. It's not as permanent as the pressing of the DVD. So there you go. I hope this has been informative. And again, if you need to reference any of the things that we breezed over, please refer back to the video on option F.2. Just one